Hello, 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 and welcome to the second part of our launch for an element of creativity, which in short is our interdisciplinary resource exploring chemistry for primary learners from P1 upwards. Can absolutely be differentiated across BGE and for community learning and development, and incorporating expressive arts and play as well. This resource consists of 5 modular lessons, 2 of which we shared yesterday at the first part of our launch, and you can absolutely catch up on still. And each one of these builds on each other, linking to the curriculum in different ways, exploring different themes, a different element of the periodic table as it was developed for the International Year of the Periodic Table, and also linking with topics and chemistry researchers who are doing work at the University of Edinburgh. Today, we are introducing 3 of the resources with the researchers behind them: Keeping Cool with Hannah Logan, Gold Phone Soup with Dr. Luke Kinsman, and Molecular Machines with Sophia and Tony. And there are lots of different ways of exploring chemistry, and the motivation for this is looking at the chemistry behind everyday life, not just the explosions and the test tubes, though we have at least one test tube in these activities today, but the fact that chemistry is creative and linked to all sorts of everyday challenges, including supporting more sustainable environments and sustainable approaches to everyday living, and also medicines, and for us to be healthy. In the resource, which will be sent to you if you are registered for this event, or you will be able to access online as well afterwards, there are the lesson plans. There are the PowerPoint slides that cover all the content, including the videos some of which we'll be showing you today, and a glossary that explores some of the chemistry elements in particular. The work was funded by the Royal Society of Chemistry as part and links to our mission as Science Ceilidh to support interdisciplinary learning, creativity, curiosity, and well-being. And so if you do like these resources, please do. There's lots more on our website as well, connecting maths to music, climate change to outdoor learning, and biology to dance. Think the Orcadian Strip, the Helix, and all that type of stuff. And that kind of that type of work brought us to this program here, where we worked very closely with our partner school, Bilston Primary, out in Midlothian, to develop these activities with our researchers, to test them out and to bring on that real experience. And so I'm really excited to first introduce and talk a bit more about the program, Phoebe Hamer, who can join us today. If I can find her, there we go. Hello, Phoebe.
Hello.
How are you doing?
I'm good, thank you. Thank you for having me.
Great to have you here. So Phoebe, could you mind telling us who you are, perhaps, and what interested you in an element of creativity in the project?
Yeah, so currently I'm the P6-7 teacher, but at the time I had a primary 2-3 class. And initially what drew me to an element of creativity was we actually met you at a science event at Dynamic Earth, and kind of listened to a lot of kind of what you were doing and what you were promoting, and instantly thought that it sounded great. I think that the kind of combination of science and expressive arts is a wonderful idea. I've got a dance background and expressive arts background before I came into teaching, and I think that it's undervalued sometimes within education, and that actually it's a really, really great tool to be able to access other areas of the curriculum. And so that really appealed to me in being able to access science and other areas of the curriculum as well, but particularly in this instance, science through other ways. And I think that the children really got on board with that, and having that kind of dual aspect was really beneficial to us.
Awesome. And that it brings a really important point to the work that we do in that, I think we're really keen to support expressive arts within the curriculum. As you say, it's very often, sadly, the first thing to go. And of course, we believe in the power of STEM. But I think, being able to build connections, and which is why we talk about interdisciplinary learning, is really important. There's an intrinsic value to arts and culture as well as there is to STEM. And there's probably more overlap than people expect in reality. And I think we really try to highlight some of the creativity of the chemists, of the work they do, and also thinking maybe about the kind of more analytical elements of the arts as well. So it works in both directions.
Yeah.
And so we worked with researchers, we worked with you, we delivered it. How was it like being on the receiving end of all these chemistry researchers and us working, doing these activities?
Yeah, brilliant. I mean, it was great to have kind of an insight into that kind of more scientific world. I think that the children definitely responded really well to having the scientists or the chemists in school. And it was very much kind of like, well, how could we possibly know anything as teachers now? These scientists were here kind of giving them the real deal. So I think that they responded really well to having them in school, but also having looked at the programme now since it's been developed, just having access to that information in kind of layman's terms and really being able to break it down in a kind of step-by-step process to deliver that is really helpful, because actually now we can recreate what our children had kind of offered to them in a classroom without needing to have a scientist there, but still have access to all that really great, like all the great resources, the videos, all the correct terminology, is really useful and actually is great to have at hand. Our children definitely responded really well to the activities. It's all very interactive and, like I say, it's very accessible and was able to be differentiated really well across our school. We had all composite classes at the time, and all children were able to access all of the workshops really well.
Thanks, Phoebe. And yeah, and I think that even building that in mind, because, we thought building blocks, which we covered yesterday, is kind of, we've aimed at a P1, but we can absolutely see it, being covered at all the levels, just to make sure that actually these subsequent sessions could build on. So it's kind of modular in that sense. And as you say, trying to make it a one-stop shop to bring in the voice of the researchers and bring in different role models perhaps as well. Thanks so much, Phoebe. I should say that if you're listening, we'd love to hear from you. So tell us where you're listening from, either live or if you're catching up. So this is from the past. Really good to get questions. We can pass them to Phoebe, and certainly when we come to our researchers as well, we'd love to hear from you. But for those who are listening, educators, youth workers, anyone who's interested, do you have any advice or sage words of wisdom, Phoebe?
I think don't be afraid to get involved. I think if you maybe science isn't necessarily an area, or STEM isn't particularly an area of the curriculum you feel confident in, or likewise dance or expressive arts isn't, don't be afraid to kind of get stuck in. It's such a great resource and the children really, really benefited from it, but actually it needed for us to be involved and kind of support and lead that. And so I think, yeah, you kind of really need to jump in with both feet and live that experience with them, because so much can be kind of got back from that. For me, definitely, there's some things that the children still remember. It's like, oh, but we did that with this mover, we did that with that dancer. Remember when we all got together and we did this part? And I think the association between the two is really apparent. And I think if you're then also involved in kind of supporting and leading that, it can only make it better. So don't let a lack of confidence in either subject area hold you back, because the resource is brilliant and actually can really guide you in that. So yeah, just get stuck in.
That's awesome. And I think there's something there about, that is the process. It's about the questions and discovering together, even with your learners, if it's new material. And as you say, even from the arts and culture perspective, that we also have a few other resources. We have like the music, for example, if that's helpful, and guides about how you can, build something and develop dance moves with the learners, very often taken from Fortnite still. I don't know how dated that is, but, whatever is meaningful, as you say, that's the point. It's embodied and they develop it and then they remember it. So it's really insightful. Awesome. Well, thanks so much, Phoebe. Hopefully we'll bring you back a little bit later and have a bit more of a chat, but really good to have you here. So that hopefully gives you a bit of a flavor of the sense of how this will, what this resource will look like, and really excited to get your feedback as well once it is out there in the world. I should also say that we are planning some CPD sessions and potentially also a forum, kind of a Google Space, for example, so that we can ask questions about if you've got questions about delivering it, and share different ideas of how it works in practice. And again, it's really important that we know that you're going to take this and make it your own, and that's exactly what we would hope to see. So we'd love to continue that conversation. We can connect you with the chemists if there's any questions about the chemistry elements of it, and obviously we can support that too. And we'd love to see what you get up to. So connect with us on social media, share with us on a hashtag, and all that type of stuff. So what is the actual resource itself? Where are we getting to? So the first off, our first resource that we'll explain today and explore a bit more is Warming Up with Hannah Logan. Warming Up explores the states of matter and what energy is, and explores a little bit about how, once we know what energy is and the different types of energy, how we can actually use that to make things more efficient and heating more efficient. Incredibly timely given the topic. So Hannah, I'm going to bring on. Hello, Hannah.
Hi everyone. Thanks for having me.
Great to have you here. I know you're busy
writing
away your experiments. It's really good to have you. Do you want to first introduce yourself and maybe tell us a little bit about kind of how you ended up in chemistry and what your background is?
Yeah, so I'm Hannah. I currently look into ways of storing heat, like a battery, but it's a heat battery instead. So I probably got into science because I've just watched a lot of science documentaries when I was a kid, Brian Cox on TV, space and things like that. And then I just sort of naturally fell into doing science when I was picking my choices in high school, and then ended up doing a chemistry degree. So I've just always enjoyed sort of being curious about things, I guess. And that's just always enjoyed that sort of aspect of science.
Brilliant. And why don't you tell us a little bit more about your research then, so about the heating element in particular?
Yeah, so my research is based around these materials called phase change materials, and they can store a large amount of heat or cold during a phase transition. So for example, the classic example that everyone would sort of understand is putting ice in your drink. So this gives out lots of cold, and this is what keeps your drink nice and cold. If you were to use another material, it wouldn't work as well as ice does, because it's got such a high energy output when it undergoes the phase transition from solid to liquid. So we use this principle to look into other materials that also have high energy storage capabilities. So you can also, while my example was about cold, you can also store heat. And we just look into ways of not only finding new materials that can store heat and cold, we look into ways of adapting these materials, making them behave better and more suitable for energy storage applications.
Really important work, again, given the rising costs of living and heating. I mean, these types of materials are going to be so important.
Yeah, absolutely. Yeah, definitely. I think it's definitely a hot topic at the moment, particularly for the company that sponsored my PhD. They do a lot of their sort of main product they uses. It's basically to replace your hot water tank, and it just means that you get cost savings and energy savings throughout the year because you're using phase change materials to store heat rather than a hot water tank and things like that. So it's really important for this sort of time when everything's getting more expensive. Savings wherever you can make it, yeah.
100%. So there's definitely the social element of that, and then again, the surprising fact that chemistry is involved in that kind of sustainability piece as well.
Yeah, absolutely. Yeah, definitely. It's nice to think that the sort of research that I'm doing is going to be making a difference to this sort of thing. Yeah.
So then, Hannah, how do we translate all that really important research into something suitable that we've designed a resource for P2s and P3s?
Yeah, so the activities that, well, in the sheet, sorry, I've got it in front of me just for reference. So so because obviously I talk about phase changes, this is a great opportunity to teach the kids about states of matter. So solids, liquids, gases. So they've got this really great activity where they can, to music, pretend to be the different states of matter, and gets them up in the classroom and moving around and pretending to be a solid, pretending to be a liquid, pretending to be a gas. So that's really good. So this is a sort of even more physicsy sort of aspect because of states of matter. And then they move on to thinking about types of energy. So obviously energy is all around them, but they might not realise different, the monitors on their TV are giving out light, but they're also giving out heat. So they get to have a discussion about what the different, all the different energies that are around them, and maybe make them more aware of that sort of thing. And the wasted energy. So like my example, we talk about, the main reason that we have TV monitors is to give out the light so that we can see the images on the screen. But if there's heat being generated, that's wasted energy. So it's just making them aware of all the different wasted energies that are around them as well. So then we bring all this together, combine it with the phase change material. So you've got the states of matter, where you've got the change from a liquid to a solid, and you're giving out energy from through heat in the hand warmer. So the hand warmer is like the really great example that really shows them. It's just such a great visual tool. It shows them the crystallization, so the freezing of the material, and then the heat given out. And I think like that was sort of like one of the standout moments for me when we did it in the classroom. They were all fascinated by these hand warmers, so it was really good. Yeah, you got one in front of. I wish I had one.
Still have many of them.
I did have one, but mine broke. Yours won't break. I've just.
But as you say, it's trying to reinforce the fact that, going from solid to a liquid or liquid into a solid will have a change in temperature. And so we, try to find these everyday materials, the things that learners might have come across. And so for this one in particular, we did actually break this down once they've learned, reinforced about the different states of matter, how this actually works. And then this is when we created the dance, right?
Yeah, exactly. So the first part of the dance, they're going to be, they click. They're going to come up with some sort of a part of the dance that represents the clicking of the disc, and this releases. Oh yeah, that's.
I can demonstrate the slide. This is on the PowerPoint.
Yep, that's helpful. So they click the disc, and this releases a little seed crystal. So it is just like a seed. And what this does is it provides a little building block for the rest of the crystals to grow from. So yeah, the video. I mean, if you see that, it's just, you can see immediately the crystallization. And that's just, I think the kids really love that. And it's just something that they can do themselves, which is quite nice. And then the crystallization process happens, and then you can see from the image there, during this changing state from the solid to the liquid, you get a large amount of heat given out. And you can see that in the heat map image there that was taken using a heat camera. So when you feel the hand warmer, it gets really hot. So that's why it's a hand warmer. You've probably all used one before or seen one before, but it's so you probably understand the principle. But then what we can then do is put the heat back into the material by melting it, and this means that you can repeat the process. So by putting the heat back in, so you can see the pot with the pan of water there, you just have to boil it up, and then once it's returned back to the liquid state, you can repeat the process again, click the disc once it's cool, and it'll work again. So so each of these steps gets broken up, and they can form a dance around these steps. And exactly. It was great, especially the part where the crystallization happens. You can imagine them all spreading out the hall and things like that. It's good.
Exactly. So I think in the guide itself, we break this down a bit slower. We encourage you to, if you do have hand warmers accessible, if not, we do have videos of this process and a video of the heat map as well, which is really cool to be able to see it happen in real time at the least, and that's embedded in the presentation. And then thinking about, as you say, how we can represent each of these steps physically as a group. And Kaylee is perfect for this because, again, 4 steps and it cycles again. So we put some suggestions in the that we help facilitate, but again, the young people might have their own ideas about how salts, how you click the disc, or how the changing into a liquid into salt might be represented.
Yeah.
Awesome. Thanks so much, Hannah. And I guess we're going to finish there, just to hopefully that gives a bit of a flavour. If you have a question for Hannah about her research or science, you can ask in the comments, and then we'll come back to you a little bit later, and we're going to introduce our next resource. But thanks again, Hannah.
Yep, thanks very much.
So we did have one comment come in, and love to hear more, but we've got Jeff talking about using singing quite a bit as a learning tool, and interested to use dance as well. And again, I think even in one of our resources, I think one that we talked about yesterday, there's the ability to bring in different elements. So writing a song to cover and rhymes to cover some of the learning outcomes as well. And that might reinforce some of the movement. So we'd love to see all these connections being made. Our next resource that we're going to introduce is with Luke, who couldn't join us here live today, but he had recorded an interview with me a couple of weeks ago. He has finished his PhD. He's now a doctor. So he was a student when we met him. But I'm going to just play the interview, and you'll get a sense of what gold phone soup involves.
I'm originally from the north of Scotland, on a place called the...
Let me try that again. So really excited to have Luke here at the moment. Luke helped develop gold phone soup with our resource and element of creativity. Luke, can you tell us a wee bit about yourself?
Yeah, hi Lewis. So I'm Luke. I'm originally from the north of Scotland, on a place called the Black Isle. I've loved chemistry since I've been in school. I was inspired to carry on studying chemistry by my aunt, who's also a chemist, and she's been designing medicines to cure various diseases. And what I've been doing is looking at how to recycle rare and precious, expensive metals from old mobile phones. In my spare time, I enjoy keeping fit, running, and playing board games and reading books.
Amazing. Thanks so much, Luke. And obviously a really relevant kind of activity. I mean, a lot of people have phones, and I think we've been really conscious about how we recycle them. And so could you tell us a bit more about your research, especially given that you're actually just about to kind of defend your PhD, the kind of some of the research that you've been doing?
Yeah, so in mobile phones in particular, there's over almost 30 different elements from the periodic table. That's the main way that chemists organize all of the elements. So almost 30 different elements go into making a smartphone. And many of these elements are precious, or they're very rare. We're running out of them. We'll be running out of them in the next 50 to 100 years. And so what we're wanting to do is try and secure the future supply of these metals, so that we can continue making not only smartphones, but other materials that we need for the future. So that's roughly why I'm doing it. Yeah.
So basically, if it means that we can hopefully keep reusing, so we don't have to keep digging up these metals, and that's explored a little bit more in the resource. There's loads of activities. We had a really good time developing this with you and delivering this in Bilston Primary. Could you tell us a bit more about what is in the resource in your own words?
Yeah, so the resource, first of all, we start off with looking at how important these metals are, what some of the metals are used for in particular. So why is gold, for example, being used in a mobile phone, and why is copper being used, and where do these elements come from the ground? So yeah, we discuss how important they are, what they're used for, and then we go on to kind of explain how we're running out of them, and some of the ways that we go about at the moment recycling them. And for some elements, we just don't have any ways to recycle them at the moment. Other ways we do. One of the main ways I look at recycling metals in the lab is a technique called solvent extraction. And so that's where we design a chemical that can selectively recognize one metal over a whole bunch of other metals in a solution. And so the resource kind of explains how that process works. And then one of the activities that we have for the students is to show them how the metals are separated from one another. And so we have a demonstration of the solvent extraction process.
Fantastic. And we convert that as well, so into, I guess, represents that physically, and I think we even developed a dance together with some of the students, and so in the resource exploring how any teacher could do the same thing and represent it physically to kind of really get under grips with it. And that's exactly the process as well that we kind of wanted to explain a bit more as well, just in terms of that, what is that activity, so that people can try the same, I guess, process, even if not using the same kind of, obviously the same kind of chemicals in that process. Could you tell us a bit more about that?
Sure. Yeah. So the process that we have, we call it extracting gold glitter from a fake foam soup. So what I do in the lab is we get a bunch of electronic waste and we dissolve all of the metals from the electronic waste into solution. And we call that a fake foam soup. It's like a soup of lots of different metals all in solution. And what you have is this dark green mixture. And so the resource, what we have the students do is we have some food coloring solution, and then we add gold glitter to that to represent the gold that's inside the fake foam soup. And then the students can then add some baby oil to the food coloring, and the gold glitter will stick to the baby oil. So they get it's demonstrated in the video that we have, but they when they shake the baby oil and the food coloring together, the baby oil separates from the food coloring and the gold glitter sticks, and that's kind of to try and represent how the gold is extracted in the real process.
Fantastic. And using hopefully things that people could access quite easily, but you demonstrating exactly the same process. And we have a video, I think, of you actually demonstrating that with the real solution and the real kind of process, which people can watch as well. One of my favorite things, actually, just random fact before we finish, is that you managed to actually extract enough gold to and put it to good use. Could you tell us a bit more about that?
Yeah, sure. So one of the attractive things about recycling metals from electronic waste is that you can actually get, in some cases, you can get more gold from electronic waste than you can from the equivalent types of rocks used to mine gold from the ground. And so one statistic is that if you have a ton of rock used to mine gold, you can get maybe 1 or 2 grams of gold if you're lucky. Whereas with electronic waste, if you're really lucky, you can get almost 300 grams of gold from a ton of electronic waste. So it's actually a really, really attractive source of not just gold, but other metals as well. And what I was able to do was I got enough, not quite a ton of electronic waste, but I got a good amount of electronic waste. And using some of the methods I've developed in the lab, I was able to get about 1 gram of gold back. And using that gram of gold, I was able to make that into an engagement ring for my partner. And I proposed, and she loved the ring, and she said yes. And it's just a lovely story.
It is. That's amazing. So what a great way of kind of bringing your research, and obviously a lot of it really pertinent at the moment as we think about how we reuse the things we have and reduce, and not extract so much from the earth, especially around climate change, around sustainability, and then lovely for you and your partner as well. So Absolutely. Thank you so much, Luke, for developing this resource with us. I hope the teachers and the learners who are watching really enjoy it. And yeah, wishing you all the very best.
Thanks, Lewis. Cheers. I hope you guys really enjoyed the resource as well. It was great fun to develop.
Brilliant. So thank you again to Luke in the past. Very, very quickly. So we've got a video. I'm not going to show all of it, but just to give you a sense of the videos that are available so that learners can actually watch Luke do this process and then be able to mimic it using kind of everyday materials, so baby oil and water, for example.
We've been able to separate the gold from our foam solution.
Just wanted to give you a flavor of that, and the whole video is going to be available that you can download in the PowerPoint. And so there was a question about the video of the dancers. Both of those resources obviously looked at exploring the concepts and then supporting your learners to develop a dance and movements to represent that. We don't have videos of that process. mostly for photo permissions reasons. And so, but what we have done is actually kind of explain what the learners did and also give some indication of what different moves you could actually do, just to kind of give a bit of an idea, and actually what moves the Bilston the Bilston learners would have also done to actually represent that. So hopefully that gives, I know visually that would be ideal, and hopefully by sharing some examples as a starting point, especially if you're facilitating that in class, is helpful just to get that going. But hopefully being able to, learners will make it their own, and which will be quite right. We're going to move to our last resource that we're going to introduce today, and this one involves two researchers, Dr. Antonia May and Dr. Sophia Bariami. And this resource is called Molecular Machines, and this one picks up particularly on the fact that not all chemistry necessarily involves test tubes and wet labs. It can, but actually can involve computers and coding to help us think about how we can design things to help medicine work better, for example. So, Sophia, we've got, and we have Tony. Welcome.
Hi, Luis.
Hello,
thank you very much for having us.
Yeah.
Great to have you both here. So I've given a bit of an idea of molecular machines, but why don't you tell us a bit more about who you are and how you ended up in chemistry as well? Tony, do you want to go first?
Sure. Yeah, hi, my name's Tony May. I'm effectively lecturer at the University of Edinburgh in chemistry, but that's actually not my background at all. I did a degree in physics, then I did a little bit of a detour via maths department, and somehow I'm now in chemistry. But basically that kind of shows the work I do is very interdisciplinary and different aspects play into it. How did I get into science? Well, I think I was always fascinated. As a little kid, I wanted to be an astronaut. I loved planets, and I think, yeah, when I was 15, 16, I was like, well, physics is probably the way I want to start out with. But I was always in the realm of trying to understand biology with physics. And that's how I ended up in what I would call biophysics, but in a chemistry department.
Brilliant, thanks, Tony. And again, you know, that journey alone maybe just demonstrates how even once people go into high school and start thinking about chemistry, biology, and physics, actually, you know, work around this issue, breaks all those boundaries down, actually, and you don't have to always pick. How about yourself, Sophia? Tell us who you are, and yeah, how you got into science?
Yeah, actually, my journey is quite similar to Tony's, with the difference that I'm not a lecturer yet. I recently finished my PhD at the University of Edinburgh. But my background is actually in maths and physics as well. During my master's, I actually found out about computational chemistry. And this is something that combined, you know, my maths, which I love, with like biology and chemistry, two subjects that I was like really interested in, you know, throughout like my, let's say, academic life so far. So it was actually through my master's degree where I found out that, oh, you know, this field exists. So there was an opportunity of, you know, going to a pharmaceutical company and doing an internship there. So I went there and I loved it. And after that, I did a PhD at the University of Edinburgh at the School of Chemistry as well, at the group of Julie Michel. And we're developing programs. We're looking at how molecules interact with each other. So yes, these 4 years have been really great. I really enjoyed it. And now I'm in Cambridge. I work in a company where we do quite similar things. So we're doing software development, and then pharmaceutical companies can actually use the software in order to develop new drugs, new medicine, to discover new molecules that can actually like help us. And yeah, so far so good. It's been a very nice experience.
Brilliant. That's really, yeah, it's fascinating. And I guess that really leads us nicely to our next question, which was, what was the research that inspired this resource, and that we, in terms of molecular machines? Sophia, do you want to kick us off?
Yeah, sure. Well, I think it was in general, you know, the concept that chemistry is not just potions and explosions, as you also mentioned before, computers are really involved nowadays. So the thing is that we wanted to show how everything is made out of atoms and molecules, how important are proteins, because of proteins we live and we exist. We also want to show the importance of the shape of the molecules in terms of like how they work, and also how computers are used to design molecules with better shape. That means molecules that have that can have like better properties, let's say, that are better medicines. So, for example, in my research, I was studying some molecular cages. That's how we call them. So imagine that we have a cage, like a host. Oh, I think you have a video of it. Yeah, there you go. And then this small molecule that you see, this cage is quite flexible, so that this molecule can get in the cage, get out of the cage, and the cage actually protects the molecule, and it can carry it within your body to specifically to the place where you want it to be. Because when the small molecule or where the drug, gets in your body, it can be lost, let's say, in quotes, it can be destroyed. So we need to protect it. And this is what this molecular cage does. So this was the inspiration of one of the activities that we did together, where we actually used pipe cleaners in order to model these molecular cages. And I was very impressed with this specific one, really, because without showing like the images, these children managed to actually like recreate like the shape of the molecular cage with a huge precision. So yes, it was a very nice activity. I really enjoyed it. So what we were trying to do is make the molecular cage and then hold the guest molecule, if I remember well, 1 centimeter from the table. Mm-hmm. So yeah, that was the activity. It was very nice.
Yeah, so you can take them crafting. I remember when you first showed me that video and put that together, the movement element of it really it wrote itself, and then the fact that we could use pipe cleaners and get creative and think about it as a challenge, and that's very much what part of the lesson plan involves.
Exactly. I think Tony has some pipe cleaners.
Yeah, I've got a little demonstration here, but it's a very poor one because the molecule actually falls out. So I did a very bad job. I'm sure the students or pupils would do a much better job than I would.
7-1, Tony.
I should have just made the ball, the molecule a bit bigger, but clearly, but it was a last minute job, so I did not give it the full attention I probably should have given it to.
No, not at all. That's great. Well, then, Tony, how about yourself? Because and this was a bit of a collaboration between you both. You do slightly different research, even though you both use computers within chemistry. So, Tony, tell us a bit more about your research and then how it informed the activities.
Yeah. So, I guess, Sophia was a PhD student in Julie Michel's group. I was a postdoc, and obviously have since moved on, just like Sophia has, but in a other direction. So I guess, the group was quite large, actually. We had 15 people at some point working it. So people in general were working on problems of how can we improve computational methods for predicting how well a drug molecule might affect a protein in our body. So think, I don't know, aspirin, how does it work? But predicting that with a computer rather than in a lab experiment. And I'm not sure if I can share this, but I kind of would like to show a video, which I should have sent you. I'm very sorry about that. So I'm not sure if this works, but we'll try it anyway.
Fingers crossed.
Yeah. Can you see this?
Yes, hold on. There you go.
Perfect. Okay, so this is basically what happens in our cells. So each of these wiggly things are proteins, and the proteins basically regulate how everything works. And this is effectively what the idea behind this molecular machines game resources, is how can we recreate this, but with students effectively. And because actually in the way we do research, we often just look at a single protein like this. So we would look at something like this, where we have a protein and we have a medicine molecule bound, or something like this, where you actually see it wiggle about. That's probably more a realistic view. But what we often forget in our research is that it actually looks a lot more like this in our actual cells. So yeah, and that kind of led to this molecular machines idea, where basically we try and build up a machine out of kids that needs to do something like move a ball from A to B, but each person has to do one type of movement, and that will help the movement of the ball. So be, I don't know, something like, we'll just do that. And that can be standing, that can be sitting, that can be big movements, that can be small movements. And it kind of explores different aspects in terms of how can you collaborate on getting something moving about, but also different aspects of movement. And that's kind of where the Kaylee aspect really comes in. And I suppose I drew the inspiration for this particular resource from the work I've done with amateur theatre. So I've been involved in a bunch of theatre groups during my PhD, but also later on I've done some improv performance work. And that was one of the warm-up games we would often play, and adapting it to a molecular machines theme seemed very appropriate.
Yeah, definitely. And I loved that you brought that in. And so I think, overall, what this resource is building on is, the building blocks that we're talking about, that's the resource picks up on Lego, the different sizes of that, getting to a protein level, and then understanding, as Tony said, that actually it's really, really messy. And so having this game where learners have to come one by one and do an action over and over again. I was thinking that we could do this online, actually. I don't know if it'll work in this 3D space, over and over, and then build the next learners to come in. Well, exactly, yeah. And then bit by bit being able to understand how that operates and have the drama element of it, the physical element of it, and actually a challenge of if you can use it to hold a ball or move a ball in the circle. Sophia, you're the last piece.
Yeah, we're waiting for you. My arms are getting tired.
That's fine. But hopefully you get a sense of it. And again, the resource talks that through about how you can actually support that. And there's actually some examples that we put in the resource of actually. So this is from the PowerPoint slide, and again explaining the lesson plan a bit more. Some different movements that actually real proteins do, and some of them do look incredibly. They walk really interesting ways, and so again using this as inspiration, perhaps for learners to use movement to represent it and build this what could end up being a very complex machine between 20, 30 learners, building up learner by learner. Brilliant. And there's one last activity that's involved in the resource. This was a bit more of a kind of a computational one. I don't know if Sophia or Tony very quickly want to mention this one.
Yeah, sure. I think that the whole idea behind it is how powerful computers are. So the children had to follow some instructions in order to solve the puzzle. And then we were counting how many solutions they found. But then the whole idea was, oh, you know what? You did great, guys, but the computer can actually find all of the solutions in like 1 second. So yes, because just like, we just want to show how powerful and how helpful computers are nowadays in like problem solving activities.
Yeah, exactly, Sophia. And so for this is, again, one of the types of resources where you can print it out, and then you might want to do as a bit of a plenary, a bit of a challenge activity. So thanks for that. Brilliant. Okay, well, that hopefully gives a bit of a flavor of molecular machines. We're really excited to share that with you very soon. I kind of want to invite questions at this point. And at this point, I might quickly bring in, finally, Hannah to come along as well. If there are any questions that you have, please throw them in the comments as we go along. And Phoebe had to run, but if there's any questions, she'll be watching and she can feed back onto the video as well. Whilst we're waiting just to check, I kind of want to go back to Hannah actually and just say, what was, you mentioned, what was your most memorable moment working with the learners?
I think it was actually just watching them do the dance for the hand warmers. I think, you know, they just seem to have so much fun doing it. And it's really nice to see them engaged in something that is scientific, but, you know, and at a level that they can understand and, just have fun with it. Yeah.
Thanks, Hannah. How about yourself, Tony?
Sorry, the mute button almost got me there. I think for me, it was just bringing lots of different elements of my life together and creating something that people actually wanted to take part in and hopefully learn something useful from it. And I guess, just playing the molecular machine game was just really fun. There was a lot of laughter, and both watching it but also being in it was great.
It was fun indeed. Yeah, I remember that.
Awesome. And Sophia, anything to add there?
Yeah, I mean, as I said before, I really enjoyed seeing how creative, you know, children can be, especially the molecular cage activity, with, you know, some groups making cages with the shape that was very similar to the one that I was actually studying. But then I think in general, I really like public engagement, but, you know, having to explain your research in school children is always, you know, so challenging, but it's also fun because you need to go to the simplest idea behind it and explain it without, you know, scientific like jargon and complex vocabulary. So it's always fun doing this.
Yeah, definitely. And I think you set us an even bigger challenge that we're not going to high school, we're going to primary as well. So
exactly. Yeah.
There's additional challenge there. But I think that's exactly why we want to do it. And something we mentioned yesterday is we know from the research that, again, it's not just about the science elements, but, you know, young people's understanding and the stereotypes about science form in primary school and are very resilient. And so this is one of the reasons why these types of activities are so important to us. I'm really excited to see how people get on. Just some comments coming in. So from Jeff, just looking forward to giving it a go and down the school. So it's nice to see science at our level, and I'll send a dance video when we do it, which will be amazing. Please do. I should also say I'll put a link into the chat. But we do have a couple of other resources out there where there are videos associated, just to give you a few ideas. And one of the resources that we have is a bit more about the strategy, about how you can use different dance movements as well. So that one is certainly linked within this resource, but is available now. So you can we'll send a link to that. And then Gail as well. So no questions, just looking forward to looking through the resource. So many thanks. Brilliant. Okay, well, that leaves me probably to end this launch. We're looking forward to catching up with you. We'll send an email out to everybody. If you've registered with us via the Eventbrite, then that way we will be able to definitely send you that, and hopefully aiming for that by early next week at the very latest. If you're watching this on repeat, or you've just caught this on, it's fell into your timeline on Facebook or Twitter, just send us a message and it will also come up onto our website as well. And we have a free mailing list for our other resources. So do keep in contact with us. And as we say, love to see them in action. And the final comment over here from Nick, really looking forward to going through the resource and getting them used in class. Amazing. All right. Well, thank you so much. Phoebe and Sophia, Hannah and Tony, and for everyone else, we wish you cheery bye. Take very good care.
Thank you.